Hey there, Sleepy Voyagers. Tonight we drift into a story about a traveller from beyond the stars. Astronomers call it Three-Eye Atlas, and recently they've realised something surprising. This interstellar visitor may be far more massive than anyone first expected. Three-Eye Atlas is the third confirmed interstellar object ever detected passing through our solar system, and that alone makes it rare. Its interstellar identity is established by a hyperbolic orbit, orbital eccentricity greater than 1. So it is not bound to the Sun and will not return once it departs. From the outset, the key story is simple but important. Imaging and photometry show that Three-Eye Atlas is active. It's producing a visible coma and tail. Yet early orbit solutions do not require a strong non-gravitational rocket, term from outgassing, to explain its motion. That combination, activity with little measurable orbital shove, pushes scientists toward the idea that the nucleus carries more mass, or has a higher mass-to-area ratio, than a first glance at its brightness might suggest. We'll unpack the details and the quantitative implications later. For this opening chapter, the aim is to lay out what that statement means, what it doesn't mean, and what to watch next. Start with what's unambiguous. Three-Eye Atlas is interstellar, on a one-pass hyperbolic trajectory. It is moving at tens of kilometers per second relative to the Sun, fast enough that planetary gravity cannot capture it into a long-term orbit. It is comet-like. Sunlight warms volatiles near the surface, gas escapes, and dust is entrained to form a diffuse coma and tail. It poses no threat to Earth. It will brighten and fade over a limited observing window set by geometry. Its distance from the Sun, heliocentric distance, its distance from Earth, geocentric distance, its angle from the Sun in our sky, solar elongation, and the Sun object observer angle, phase angle. Why not simply measure its size and call it a day? Because the nucleus is veiled by its own activity. The coma's dust light overwhelms the unresolved core in most images, so any nucleus size you see early on is almost certainly an upper limit. Photometric size estimates depend on albedo, how reflective the surface is, phase function, how brightness changes with angle, and the amount of dust in your aperture, quantities that are uncertain at first. This is why dynamic clues, tiny accelerations or the lack thereof, become so valuable. They provide constraints that are independent of how shiny or dusty the object is. Here is the essential physics behind the more massive than expected phrase you're hearing. Outgassing imparts momentum to the nucleus. In orbit fits, that recoil usually shows up as small systematic departures from a pure Keplerian path. If you can see the coma and tail, you know gas and dust are leaving. If you cannot detect the corresponding orbital nudge at the sensitivity of the current data, you can place an upper limit on that acceleration. Combine that upper limit with even conservative assumptions about mass loss rates and gas speeds, and you get a lower limit on the nucleus mass. If that lower limit sits comfortably above what naive brightness-only arguments would allow, the object earns the more massive than expected label, provisionally. Provisional is an important word. There are alternative explanations for small or undetected recoil. The active areas could be arranged in a nearly symmetric way around the spin axis, with jets cancelling each other's pushes across a rotation. The outflow speed could be lower than standard thermal models would predict at the observed distances, reducing the momentum carried away for a given amount of gas. The activity could be dominated by a few localized vents that point in directions that minimize a long-track acceleration. And it is always possible that the data sampled so far are simply not sensitive enough to the specific component of acceleration that matters most for the orbit, typically the long-track component. In other words, more massive than expected is a working interpretation that competes with more symmetric or slower jets than expected. Distinguishing between those scenarios is exactly what the next wave of observations is designed to do. What then should you keep in mind about Three-Eye Atlas right now? First, it is an active comet-like interstellar traveller, which is scientifically gold. Active means spectroscopy can probe gases, what volatiles are driving the show, and photometry can track dust production over time, both of which teach us about formation conditions in another planetary system. Second, hyperbolic means the clock is ticking. The object will be accessible for a limited time before geometry worsens and it fades beyond practical reach. Third, the mass narrative is not about a single dramatic number. It's about whether the orbit requires non-gravitational terms and, if not, how strong a lower bound on mass we can deduce when that lack is combined with the directly observed activity. There are a few concrete signals to watch for as the story develops. If the rotation period can be measured from repeating jet structures or a coma-corrected light curve, and it remains stable through peak activity, that stability favours either a larger moment of inertia, which goes with more mass and/or a larger radius, or a very symmetric jet configuration. If instead the period shortens or lengthens measurably, that indicates significant torques from uneven venting, which can relax the mass inference. If high-resolution imaging and careful coma subtraction reveal a brighter unresolved core than expected, size estimates move upward. If they push the nucleus upper limit downward, the massive claim must be supported by density rather than size, or it must weaken. And if orbit fits begin to require a coherent along-track acceleration that scales with solar distance in a way consistent with standard sublimation laws, the mass lower bound will drop accordingly. For observers, professional and advanced amateur, the practical bottom line for this phase is straightforward. Expect 3i Atlas to remain a faint, low-surface brightness tend target, better suited to telescopes than naked-eye viewing. Plan around solar elongation and altitude for your sight and treat it like a dim galaxy, low to moderate magnification visually, and short, repeated exposures for imaging, preferably with non-sidereal tracking or comet line stacking. If you are doing photometry, keep your aperture consistent in arc seconds and report your aperture radius and filter. If you're exploring morphology, note the position angle of the tail and any jets, and document changes across sessions. All of those small details are the raw materials that eventually inform the mass and dynamics conversation. Stepping back, why does any of this matter beyond this single object? Because 3i Atlas is a data point in the emerging field of interstellar small bodies. Each new visitor helps calibrate how frequently planetary systems eject planetesimals, what ices and dust structures survive long interstellar journeys, and how activity translates into momentum. Transfer in different chemistries and textures. The more massive than expected discussion is not a curiosity, it's a probe of internal structure, porosity, and vent distribution in material that formed under a different star. 3i Atlas is the formal designation for the third confirmed interstellar object identified passing through the solar system. The 3i label marks it as the third of its kind, I for interstellar, and Atlas credits the wide field survey that first flagged it. Its interstellar nature is established by a hyperbolic trajectory, orbital eccentricity greater than 1, which means it is not bound to the Sun and will exit the solar system after a single flyby. As currently observed, 3i Atlas behaves like an active comet-like body. Imaging and photometry show a diffuse coma and a developing tail produced by the sublimation of volatile ices when sunlight warms the surface. That activity distinguishes it from a purely inert asteroid-like object and places it closer, phenomenologically, to the second interstellar visitor, which was an ordinary-looking comet, than to the first one, which lacked a detectable coma. Because the nucleus is hidden inside a bright dusty envelope, estimates of its physical size rely on indirect methods. Analysts combine apparent brightness with assumptions about reflectivity albedo, dust contribution, and viewing geometry. Early constraints generally point to a nucleus in the kilometre scale, but the uncertainty is substantial until the dust production rate and phase angle effects are modelled more precisely. Colour measurements, Gibel broadband indices, are typically consistent with the slightly reddish-dark surfaces common among long-period comets, though coma contamination can bias those colours. The dynamical picture is straightforward. 3i Atlas entered the solar system from interstellar space on an inbound hyperbola, will pass its perihelion, closest approach to the Sun, and then depart on a different outbound hyperbola. Its asymptotic speed at large distance is in the tens of kilometers per second regime, fast enough that no planet can capture it into a long-term orbit. High inclination with respect to the ecliptic is unsurprising for an object drawn from the random orientations expected of the galaxy's background population. A central technical focus is whether the orbit requires non-gravitational acceleration terms, tiny rocket effects caused by outgassing jets. Many active comets show measurable deviations from purely Keplerian motion due to this thrust. If the best fit solutions for 3i Atlas do not need such terms, or only need very small ones, yet the object clearly displays activity, then the implied mass-to-area ratio is comparatively high. That inference underlies the current discussion that 3i Atlas may be more massive than initially assumed for an object of its brightness. This remains provisional and depends on the growing astrometric arc, measurement precision, and realistic jet geometry models. Spectroscopically, observers will target common volatile traces and dust features to characterize composition. Typical detections for active comets include emissions from radicals such as Cn and C2, and continuum from dust scattering. At infrared wavelengths, CO and CO2 bands can constrain the drivers of activity at larger heliocentric distances, where water ice is less efficient at sublimating. Measuring the ratio of different volatiles, as well as polarization and grain-size distributions in the dust, helps compare 3i Atlas to solar system comets and to the earlier interstellar example. Rotation state and shape are harder to nail down while the coma is bright. Light curve variability can reveal a rotation period, but activity tends to dilute the amplitude. Where possible, observers will attempt coma subtraction or use high-resolution techniques to isolate nucleus signals. Any reliable period combined with size estimates would bound the object's bulk density and internal strength. A low-density, porous aggregate would behave differently under outgassing than a compact, higher-density nucleus. This ties directly into the mass discussion. From a practical observing standpoint, 3i Atlas is expected to remain a faint target for large amateur and professional telescopes. The best data come from stacking long exposures for astrometry and from spectroscopy on larger apertures. Viewing geometry, solar elongation, phase angle, and lunar interference will govern windows of opportunity. Space-based facilities can mitigate atmospheric limitations and push to fainter features in gas and dust. Scientifically, 3i Atlas is valuable because it offers a composition and structure data point from a planetary system other than our own. Interstellar small bodies are thought to be ejected during planet formation or later dynamical reshuffling. Their surfaces record processing by cosmic rays and thermal cycles under a different stellar spectrum. Comparing its density, volatile inventory and dust properties to solar system comets tests formation models and informs how common certain ices and textures are in the galaxy. Key uncertainties at this stage include the true nucleus size, bulk density, detailed composition, rotation period, and the magnitude, if any, of non-gravitational accelerations. As the observational arc lengthens before and after perihelion, orbit fits will tighten, coma models will improve, and any conclusions about mass and density will become more robust. For now, the secure statements are that 3i Atlas is an active comet-like interstellar object on a hyperbolic path, likely in the kilometer-scale size regime, and currently under intensive monitoring to determine how its activity couples, or does not couple, to its motion. 3i Atlas follows a hyperbolic one-pass trajectory through the solar system. Hyperbolic means its orbital eccentricity is greater than 1, so it is not gravitationally bound to the Sun and will not return once it departs. The path is described by a standard set of orbital elements: perihelion distance, its closest point to the Sun, inclination, tilt relative to Earth's orbital plane, longitude of the ascending node, argument of perihelion, and the time of perihelion, As additional astrometric measurements come in from multiple observatories, these elements are refined and the formal uncertainties, typically expressed as a covariance matrix, shrink. Early solutions can move around noticeably. With a longer observational arc, the ephemeris stabilizes. From a dynamic standpoint, the flight plan can be thought of in 3 phases. Inbound leg from interstellar space, a rapid swing through perihelion, and the outbound leg back to interstellar space. Far from the Sun, the object's motion is well approximated by a straight-line asymptote with an excess velocity, often called v infinity, of tens of kilometers per second. Near the Sun, solar gravity bends the path. After perihelion, the object departs on a different asymptote set by that deflection, and by any small perturbations accumulated along the way. Gravitational perturbations from planets are modelled in all precise solutions, but for an interstellar object moving this fast, encounters are brief and deflections from planets are modest unless there is a very close approach. Analysts monitor the minimum orbit intersection distance, MOID, with major planets, especially Earth and Jupiter, to check for potential close passes. Current solutions emphasize that there is no impact risk to Earth. Even when no hazardous encounters exist, small planetary tugs subtly rotate the outbound direction and slightly change the outbound speed in the heliocentric frame. Because 3I Atlas is active, shows a coma and tail, modelers also consider non-gravitational acceleration, tiny thrusts from outgassing jets. In comet orbit fitting, these are commonly parameterized as radial, transverse, and normal components relative to the orbit. Whether those terms are required depends on how precisely the astrometry can be fit by gravity alone. If non-gravitational terms are negligible or very small, the predicted sky path remains largely a function of gravity plus measurement noise. If they're significant, predictions must include a thermal model of activity versus solar distance to avoid systematic errors. The apparent motion against the stars accelerates as 3I Atlas approaches perihelion and decelerates on the way out. For observers, the key practical quantities are solar elongation, the angle from the Sun, phase angle, Sun object observer, and topocentric rate of motion, arc seconds per minute. When the solar elongation is small, the object is lost in twilight or too near the Sun to observe safely. When it increases, observing windows open either in the morning or evening sky, depending on geometry. A high inclination can move the track well off the ecliptic, so visibility favours different hemispheres at different times. Professional teams generate nightly ephemerides that include right ascension, declination, rate of motion, positional uncertainty, and brightness estimates to plan exposures and telescope tracking rates. Brightness along the flight plan follows the usual comet-like behaviour, roughly proportional to inverse square of heliocentric distance for sunlight received, with an additional dependence on geocentric distance and activity level. Because 3I Atlas is actively producing dust and gas, its magnitude is not determined by a bare nucleus alone. Dust production can brighten it, while phase effects and dust properties can change how efficiently it scatters light. This is why predicted magnitudes often come with larger uncertainties than positions. Another active area is precovery and postcovery. Teams search existing image archives for faint, earlier appearances of 3I Atlas near the inbound leg that were not recognised at the time. Even a handful of precovery points can extend the time baseline by weeks or months, dramatically tightening the orbit and improving forward predictions. Similarly, continuing astrometry on the outbound leg helps test for any slow drift due to non-gravitational effects that might have been hidden by noise earlier. Trajectory solutions are produced in heliocentric or barycentric frames. High-precision work applies light-time corrections because the object is observed where it was when its light left. Stellar aberration and topocentric parallax, the small shift due to the observer's location on Earth. For very fast movers like 3I Atlas, these corrections are routine but essential to keep residuals, the differences between observed and calculated positions, at the subarc second level needed to detect tiny accelerations. predictively, the most uncertain interval is around peak activity near perihelion, when jetting, if present, can be most variable. Orbit teams often publish both a purely gravitational solution and one or more solutions with candidate non-gravitational parameters to bracket possibilities. As new observations arrive, one branch typically wins out and subsequent predictions consolidate around that solution. Up close, 3i Atlas presents the classic signatures of an active comet, a central condensation embedded in a diffuse coma and one or more tails whose geometry changes with viewing angle and solar distance. The coma is a cloud of gas and dust released as volatile ices near the surface sublimate under sunlight. In simple, steady outflow, the coma's surface brightness profile falls off roughly, as the inverse of projected distance from the centre. Departures from that trend often indicate changing activity, jets, or grain evolution. The tail system typically separates into an antisolar dust tail, governed by radiation pressure, and a fainter dust trail aligned more closely with the orbit, composed of slower, larger particles. Morphologically, the most diagnostic features are jets and fans, localized outflows that rotate with the nucleus and can create corkscrew or sector-shaped patterns. Analysts track the position angle of the tails and measure isophotes, contours of equal brightness, in deep images to see whether 3i Atlas exhibits axisymmetric flow or structured emission. Mapping those structures against time and comparing them to models of dust motion under solar gravity and radiation pressure constrains the directions of active areas on the surface and the spin axis orientation. Dust dynamics are summarized by the radiation pressure parameter, often called beta, which is roughly the ratio of radiation pressure to solar gravity for a grain. Small, fluffy grains have higher beta and get pushed into sharper, more curved tails, while larger, compact grains, low beta, cling to the orbital direction. When observers detect a curved dust tail plus a straighter orbit-aligned feature, it points to a mix of grain sizes being released by 3i Atlas. The curvature and thickness of these structures, along with their brightness, allow teams to estimate typical grain sizes, ejection speeds, often tens to hundreds of meters per second for micron to sub-millimeter grains, and the total dust mass leaving the object per second. Photometrically, the coma and tail dominate over the unresolved nucleus in most images. To quantify dust production in a way that is less sensitive to aperture choice, observers use the AFRHO metric. A is albedo, F is filling factor, RHO is the photometric aperture radius projected at the comet. AFR acts like a proxy for the column density of dust and is compared across epochs and comets. Because dust scattering depends on phase angle, the Sun-Comet observer geometry, brightness measurements are often corrected with empirical phase functions to place different observations on common footing. Colour indices measured in broadband filters tend to be slightly redder than the Sun, consistent with typical cometary dust. However, coma contamination means these colours reflect the dust and gas mixture, not the bare surface. Polarimetry, measuring the degree and angle of linear polarization of scattered sunlight, adds another layer of close-up insight. The polarization phase curve, polarization versus phase angle, responds to grain size, porosity, and composition. A higher polarization at certain phase angles suggests more porous, aggregate-like grains, while lower polarization at the same angles can imply more compact particles or different size distributions. Comparing 3i Atlas's polarization behavior to that of solar system comets helps determine whether its dust is broadly similar or systematically different, an important clue to the environment in which it formed. Spectroscopically, the visible and near UV coma commonly shows emission features from photodissociation products like CN and C, two superimposed on a dust reflection continuum, while the near IR can reveal fundamental bands of CO and CO2 that directly trace drivers of activity at larger heliocentric distances. Measuring these species production rates and ratios, the CO/CO2/H2O proxies, is a primary objective because they diagnose the volatile budget powering the coma. If 3I Atlas shows strong CO or CO2 relative to water, that would indicate activity triggered at lower temperatures and could hint at formation conditions different from many inner solar system comets. Estimating the nucleus size beneath the coma is one of the most challenging close-up tasks. The standard approach is point spread function fitting and coma subtraction. Model the coma with a radial profile, subtract it, and see whether any unresolved core remains above the residuals. Space or adaptive optics imaging helps by shrinking the stellar PSF, but even then, bright comae can swamp the nucleus. Converting any residual flux into a size requires assuming a geometric albedo, often around a few percent for dark cometary surfaces, and accounting for phase effects. Presently, the most robust statements are upper limits and order of magnitude estimates, typically indicating a nucleus in the kilometre range, with wide error bars until activity ebbs or high contrast imaging isolates the core more cleanly. Rotation and shape information are encoded in time variable features. In a perfect world, a nucleus light curve would reveal a rotation period via periodic brightening and dimming. In practice, the coma damps the nucleus signal. Instead, analysts watch for repeating jet patterns, asymmetric coma sectors that drift with time, or small periodic changes in gas and dust production, as the sun illuminates different longitudes. If a repeatable pattern is found, it can yield a rotation period and, when combined with jet modelling, a pole orientation. Knowing the rotation state matters because it controls seasonal effects, how quickly new regions warm, when frost lines migrate, and whether localised outbursts occur as fresh active areas rotate into sunlight. The microphysics near the surface of 3I Atlas governs much of what we see up close. If a dust mantle forms, an insulating lag of non-volatile grains left behind as ices sublimate, it can choke off underlying ices until cracks open or thermal stresses disrupt the crust. Low thermal inertia, powdery porous material, allows rapid temperature swings and can favour episodic activity, while higher thermal inertia, more compacted or sintered material, smooths the response to solar heating. Outgassing through vents can entrain dust efficiently, creating narrow jets. Diffuse activity suggests broader patches of sublimation or gas percolating through a porous matrix. These scenarios leave different signatures in coma profiles and jet morphology. Gas and dust production also feed back into dynamics. If 3I Atlas emits material anisotropically, momentum conservation imparts tiny non-gravitational accelerations. Detecting or constraining those accelerations requires exquisitely precise positions over weeks to months, but the morphology helps interpret them. A dominant, persistent jet aligned with a stable direction could produce a measurable transverse or radial thrust, while symmetric activity would tend to cancel out. This is why imaging, photometry and astrometry are analysed together rather than in isolation. High-resolution imaging from large ground-based telescopes and from space can sometimes reveal features within a few hundred kilometres of the nucleus. Sunward fans, neckline structures from previously emitted grains crossing the orbital plane, or multiple jets that come and go with rotation. Image processing techniques, e.g. azimuthal median subtraction, division by a 1 over row profile, or unsharp masking, enhance low-contrast structures without inventing spurious detail when applied carefully. Repeated sequences over hours can turn static snapshots into diagnostics of rotation and source region latitude. From an observer's standpoint, getting the best close-up data on 3I Atlas involves choosing photometric apertures that balance signal against contamination, tracking at the comet's non-sidereal rate to avoid trailing, and scheduling runs at high solar elongation and dark skies to reduce background. Narrowband comet filters isolate gas emissions for production rate estimates, while broadband filters constrain dust color and help compute AFRECHO. Polarimeters require stable conditions and careful calibration, but even a few high-quality points along the phase curve are extraordinarily informative. For spectroscopy, the signal is faint. Larger apertures and longer integrations are often needed, especially for CO and CO2 in the infrared. Comparisons to familiar comets help frame expectations. Many long-period comets display similar red and dust colours, 1 over rho-like coma profiles, and jet activity near perihelion, but the relative strengths of gas bands, the dust size distribution, and the volatility budget can vary widely. The significance for 3I Atlas is that any systematic differences, grain porosity, unusual volatile ratios, persistently weak or strong non-gravitational effects, could reflect formation and processing in a different stellar nursery. If its dust proves more compact or unusually porous, if its gas chemistry is atypical, or if its activity turns on or off at solar distances that don't match standard thermal models, those would be tangible clues that we are seeing material assembled under different conditions than those common in our own comet reservoirs. Uncertainties remain substantial and are part of the close-up picture. Separating nucleus light from coma light pushes image modelling to its limits. Deriving grain sizes from tail curvature depends on assumptions about ejection speed laws and grain optical properties. Gas production rates can be biased by fluorescence efficiencies and aperture choices. Still, as more observations accumulate across a range of phase angles and heliocentric distances, the ensemble of techniques, photometry, spectroscopy, polarimetry, morphology, and precise astrometry converges. Each refines a different piece of the puzzle: what the surface is made of, how it releases material, how the dust is constructed, and how all of that shapes the look and behaviour of 3I Atlas at close range. In the near term, the most informative developments to watch are any emergence of stable jet features, changes in coma slope with solar distance, the behaviour of the polarisation phase curve, and improved upper limits, or a direct detection, of the nucleus in high-resolution data. Together, these will tell us not just how 3I Atlas looks, but why it looks that way. Linking the visible structures in its coma and tail back to surface physics, internal properties, and ultimately the environment where this interstellar traveller first took shape. This is where we lay out the core claim and the reasoning behind it. The available measurements suggest that 3I Atlas is more massive than initially assumed for an object of its apparent brightness, and that conclusion comes from converging orbital and physical diagnostics rather than a single dramatic measurement. Start with the mechanics. An active comet vents gas and dust when sunlight heats volatile ices. That venting acts like a very small rocket engine. The mass leaving the surface carries momentum, and conservation of momentum imparts a recoil acceleration to the nucleus. In orbit solutions, this rocket effect shows up as tiny systematic departures from a purely gravitational path. Analysts parameterize it in 3 orthogonal components relative to the orbit: radial, a long track, and out of plane, scaled by a standard sublimation law that grows as the comet approaches the Sun. If you clearly detect those non-gravitational terms, you can infer how strongly the outgassing is pushing the body. If, on the other hand, you see activity in images, coma and tail, but the orbit still fits cleanly without invoking a measurable recoil, you are pushed toward a higher mass-to-area ratio for the nucleus. In simple terms, with the same level of venting, a heavier object shifts less. That logic is the backbone of the more massive than expected description for 3I Atlas. Early astrometry, positions measured precisely against background stars, can be explained to high accuracy by gravity alone, or at most with very small recoil terms, despite the fact that photometry and imaging show a real sustained coma. The combination of visible outgassing plus little to no orbital shove is unusual enough to prompt mass inferences that sit above conservative first guesses made solely from brightness. To connect this to physical quantities, consider the momentum balance. The outgassing thrust is roughly the product of the mass loss rate and the exhaust speed of the gas, with dust entrainment contributing additional momentum. The acceleration on the nucleus is that thrust divided by the nucleus mass. Put schematically, acceleration approximately equals m dot v jet over m, where m is the total mass emitted per second V-jet is the characteristic outflow speed near the vents, and m is the nucleus mass. Orbital fits apply an upper limit on acceleration if they don't require a non-gravitational term. Imaging and spectroscopy constrain m' and V-jet within broad ranges. Rearranging gives a lower limit on m. Even with conservative assumptions for m and V-jet, the absence of a detectable orbital shove implies a nucleus mass comfortably above minimal lightweight scenarios. Brightness alone cannot settle the question because the coma dominates the light and is influenced by dust production, dust properties, and geometry. A compact nucleus with vigorous dust release can look as bright as a larger nucleus with modest dust, so analysts do not lean on naked magnitude to declare a high mass. Instead, they cross-check multiple independent indicators, non-gravitational acceleration constraints. Fit residuals in the orbit solution remain small without the need for significant recoil terms, leading to low upper bounds on the allowed acceleration. Tighter astrometric arcs and coverage around perihelion further shrink those bounds. The stricter the bound, the larger the implied lower limit on mass, given any plausible outgassing. Spin state stability. Outgassing not only pushes the comet's centre of mass, it also exerts torques that can change the rotation rate. If repeated photometry once corrected for coma fails to show the kind of spin-up commonly seen in smaller lighter comets with asymmetric jets, the consistency bolsters the picture of a nucleus with a comparatively large moment of inertia. Stable or slowly changing jet geometries can weaken this inference, but a lack of measurable spin change during peak activity sits more comfortably with a higher mass, or a very symmetric jet configuration. Activity level versus orbital response. Dust production proxies like AFRHO and gas production diagnostics indicate real activity. If those production rates reach levels that other comets correlate with detectable recoil. Yet 3I Atlas remains dynamically quiet. The simplest explanation is a larger than expected mass for the same cross-section of sunlight. From there, you can translate massive into concrete nucleus scenarios. Typical cometary bulk densities range from roughly 0.3 to 0.8 grams per cubic centimetre, high porosity to moderately compact. A spherical nucleus with a 1 kilometre radius at 0.5 grams per cubic centimetre would weigh on the order of 2 times 10 to the 12th kilograms, about 2 billion tonnes. Double the radius to 2 kilometres and mass climbs by a factor of 8, into approximately 1.6 times 10 to the power of 13 kilograms, about 16 billion tonnes. If the mass inferences for 3I Atlas, based on the weak recoil and sustained activity, push us toward the upper end of such ranges or beyond, it implies either A, a larger nucleus than the most conservative brightness-based estimates, B, a higher bulk density, more internal strength or less porosity, C, a low active fraction, where most of the surface is inert and only small areas vent strongly, reducing effective recoil per unit mass, or D, some combination of these. Each of those options can be tested, larger nucleus. This would eventually be supported by high-resolution imaging and careful coma subtraction, yielding a brighter unresolved core than expected, or by thermal IR constraints that favour a bigger emitting area at given temperatures. Higher density, harder to prove directly but consistent with weak spin-up, reduced shape change under activity, and possibly different fracture behaviour. For example, fewer outbursts despite solar heating. Low active fraction. Morphology would show discrete, persistent jets rather than broad surface-wide activity. Gas production rates relative to dust might appear uneven if vents are localized. Important caveats temper the claim. The absence of a detected non-gravitational term does not automatically mean very massive. It could mean that jet geometry is unusually symmetric, so the pushes cancel over a rotation. It could mean that activity levels, while real, are still modest compared to the epoch when measurements were most sensitive. It could reflect observational selection, with the densest astrometry coming from geometry least favourable to detecting small along-track drifts. Or it could be that the sublimation law used in the fit does not capture the true thermal response, smearing out the signal. Analysts therefore treat the more massive conclusion as a lower bound inference that must survive more data. The timeline matters. As 3I Atlas approaches and then recedes from perihelion, venting patterns and total production can change, sometimes abruptly. That's the window when small non-gravitational accelerations, if present, are most likely to become measurable. If, after this high activity interval, orbit fits still do not require recoil terms beyond extremely small values, the mass inference strengthens. Conversely, if a coherent along-track drift appears that scales with the expected thermal response, the permissible mass range shifts downward accordingly. Another check comes from the area-to-mass ratio. Some small bodies, especially thin or very low-density fragments, exhibit measurable radiation pressure accelerations. For a kilometre-class bulk nucleus, radiation pressure is negligible. Any detectable solar radiation push would imply an improbably large cross-section per unit mass. The lack of such a signal in fits is consistent with a compact, relatively massive body rather than a low-density sheet or aggregate. Putting the strands together, the current state of play looks like this. 3I Atlas is unambiguously active and unambiguously interstellar. Its photometric behaviour fits a comet-like object emitting dust and gas. Its orbit, so far, does not show the magnitude of non-gravitational acceleration commonly associated with similarly active bodies of modest mass. Reasonable combinations of gas/dust production and jet speeds, when set against tight dynamical limits, imply a nucleus mass on the high side of first-pass expectations from brightness alone, pointing to either a larger effective size, a higher bulk density, a smaller active fraction, or a mix of these. The outstanding questions are exactly how large the nucleus is, how dense or porous its interior may be, how the active areas are distributed, and whether the spin state remains stable through peak heating. What would strong confirmation look like over the next observing windows? 3 things. 1. A persistently negligible non-gravitational term in high-precision orbit fits spanning pre- and post-perihelion. 2. Lack of measurable spin rate change despite continued activity. And 3. Independent size constraints trending to the upper end of the current range. Any 2 of those 3 outcomes would make the more massive than expected label very hard to argue against. On the flip side, a clear detection of a long track drift scaling with solar distance, or a robustly small nucleus diameter from high contrast imaging, would tighten the mass downward and shift the narrative towards symmetric jetting or low active fraction rather than high mass. In short, the reveal is not a single number but a pattern, activity without commensurate orbital recoil, stable or slowly changing rotation, and physical constraints pointing to a nucleus that carries more substance than conservative brightness-based assumptions would have given it. That is why 3I Atlas is being characterized as more massive than expected, and why the next wave of astrometry, photometry, and high-resolution imaging is so important to lock that conclusion in or refine it. The claim that 3I Atlas is more massive than expected carries several concrete implications, but each comes with caveats that deserve equal emphasis. Start with first-order physics. If the nucleus mass is high for its apparent brightness, you are generally looking at one or more of these conditions. A larger nucleus than the conservative brightness-based estimates would suggest. A higher bulk density, less porosity or more internal strength. A smaller active fraction of the surface, so jets originate from limited areas rather than the whole body. Lower than assumed jet speeds, or unusually symmetric jetting that cancels thrust. Each pathway predicts different, testable signatures in the photometry, morphology, spectroscopy, and dynamics. A larger nucleus should gradually reveal itself through improved coma subtraction and thermal constraints. When the coma is bright, point spread function fitting often yields only an upper limit, but as geometry improves or activity wanes, a residual unresolved core can emerge. Translating that core brightness into size still depends on albedo and phase function, both notoriously uncertain for dark, dusty bodies, a steadily increasing lower bound on diameter, once independent teams reproduce it, would support the larger body branch of the inference. A higher bulk density has subtler fingerprints. Cometary densities in the solar system cluster at low values, implying high porosity. If 3I Atlas sits significantly above that range, you might expect less rotational acceleration from outgassing torques, fewer large amplitude changes in light curves even during strong activity, and potentially fewer fragmentation events despite thermal stresses. None of these is a smoking gun on its own, they gain strength together. Caution: a symmetric jet configuration can mimic the dynamical effects of high mass by cancelling torques and thrust without requiring a dense interior. A small active fraction naturally explains activity without much shove. Localized vents can produce a visible coma and tail, yet the net recoil averages down over a rotation if sources are distributed in offsetting directions, or if the spin axis geometry keeps jets roughly balanced. Morphologically, this tends to generate persistent directional features, fans, jets, rather than a smooth quasi-isotropic coma. Time-resolved imaging that tracks repeatable jet position angles across many rotations is the way to quantify that. If the jet map shows near symmetry about the spin axis, the expected recoil can be small even with robust production rates. Jet speed assumptions matter. The acceleration on the nucleus scales with mass loss rate and outflow speed. If gas velocities or dust loading are lower than standard prescriptions near the heliocentric distances sampled so far, the same visual level of activity would impart a smaller push. That in turn weakens the lower limit on mass derived from non-detections of orbital recoil. The thermal driver also matters. If activity is dominated by CO or CO2 at larger distances, the usual water-driven scaling used in orbit fits can miss time when thrust should peak. Mismodel the sublimation law, and you can under- or overestimate the non-gravitational terms. Astrometry is a powerful arbiter here, but it is not immune to systematics. Residuals at the few tenths of an arcsecond level can hide or mimic tiny accelerations unless reference frames, colour-dependent refraction, trailing corrections, and centroid biases from asymmetric comae are handled consistently. Sensitivity to along-track accelerations is geometry-dependent. Data concentrated near specific viewing configurations can leave degeneracies in the fitted parameters. Extending the observational arc well before and after perihelion, and sampling a range of phase angles, reduces those degeneracies and turns non-detection into a meaningful bound. Photometric proxies for dust production, like AFRO, must be interpreted carefully when linked back to dynamics. AFR is shaped by grain size distributions, albedo, and phase effects. Two comets with the same AFR can differ considerably in gas production and dust kinematics. If 3I Atlas happens to favour larger, slower grains, you could see a bright dust coma with relatively modest momentum flux. Conversely, fine, fast grains carry more momentum per unit mass loss, strengthening the expected recoil. Direct measurements of gas species, the dust-to-gas ratio, and grain velocities from tail curvature modelling are crucial to break that degeneracy. Rotation is the second diagnostic lane. Outgassing torques often spin small comets up or down measurably over weeks to months, especially near perihelion. If repeated, coma-corrected photometry and jet pattern tracking show little or no change in the rotation period of 3I Atlas through peak activity that aligns with a larger moment of inertia, higher mass and/or larger radius. But again, symmetry can counterfeit mass. Event geometry that applies torques in alternating directions across a rotation can yield a small net effect even on a lightweight body. Locating active regions in latitude and longitude via jet modelling helps separate these cases. Thermophysical behaviour near the surface adds nuance. A low thermal inertia substrate, fluffy porous material, responds quickly to changing sunlight, often producing spiky activity tied to the diurnal cycle. A higher thermal inertia, more compact or sintered material, smooths the response, which can moderate jet variability and torque fluctuations. If 3I Atlas shows unusually steady activity profiles for its solar distance, a denser or more consolidated near surface could be implicated, consistent with, though not proof of, a higher bulk density scenario. Radiation pressure constraints on the nucleus are a sanity check. Significant acceleration from solar photons would only be detectable for very low mass-to-area ratios, thin fragile aggregates or sheet-like fragments. The absence of such a signature is consistent with a compact three-dimensional nucleus. That does not prove massive, but it rules out some extreme low-mass geometries that might otherwise masquerade as a cometary coma. What would significantly reinforce the more massive interpretation over the coming months? 3 independent threads converging. 1. Orbit solutions spanning pre- and post-perihelion that still do not require non-gravitational terms above very small thresholds. 2. Rotation period measurements that remain stable within tight limits despite sustained activity. And 3. Improved size constraints that either push the nucleus radius toward the upper end of current estimates or deliver thermal infrared effective areas incompatible with a tiny core. If 2 of these 3 line up strongly, the high mass conclusion becomes hard to dispute. Conversely, what would pull the mass back down? A clear, statistically significant along-track drift that scales with solar distance according to a plausible sublimation law, detectable spin-up consistent with asymmetric jetting, or a robustly small nucleus diameter from high-contrast imaging or stellar occultation work, once albedo assumptions and phase effects are factored in. Any of these would shift emphasis toward geometry and modelling choices rather than intrinsic mass. Finally, it is worth highlighting the scientific stakes of getting this right. If 3I Atlas truly carries more mass for its brightness than the median comet in our catalogues, that informs how interstellar small bodies are selected for ejection from their home systems. Massive, compact objects might be preferentially launched by close encounters with giant planets, or they might simply survive interstellar processing better than fragile aggregates, biasing what we can discover. The volatile mix would then tell us not only about where it formed in its natal disk, but also about how robustly different ices and pore structures endure long exposures to cosmic rays and thermal cycling between star passages. If, on the other hand, the massive label fades with improved modelling, we will have learned something just as important: that careful treatment of jet symmetry, thermal drivers, and observing geometry can fully account for the early dynamical quiet, narrowing the physical parameter space without invoking unusual mass. The prudent stance, then, is balanced confidence with quantified uncertainty. Treat the current evidence as a lower bound on mass derived from small or absent non-gravitational accelerations. Cross-check it against evolving size and rotation constraints, and keep alternative explanations, jet symmetry, active fraction, thermal law mismatches, on the table. As the dataset grows, posterior estimates on mass, density, active fraction, and jet speeds will tighten together rather than in isolation. When those pieces settle coherently, we will know whether 3I Atlas is genuinely heavy for its look, or simply well arranged to hide its pushes in plain sight. Scientists are excited about 3I Atlas because each interstellar object is the direct sample of solid material formed around another star, delivered to us without a spacecraft. With only a handful of confirmed interstellar visitors so far, every new one dramatically expands the comparative dataset. 3I Atlas adds a critical point because it behaves like an active comet, giving access to both volatile gases and solid dust, 2 complementary windows into the chemistry and physics of small bodies formed beyond the Sun. The volatile inventory is a primary target. By measuring production rates of common species, for example water-derived radicals alongside carbon-bearing molecules, and tracking how those rates change with solar distance, researchers can infer what ices dominate the surface and near subsurface. If 3I Atlas shows strong activity from species that sublimate at relatively low temperatures, that supports a formation or long-term storage environment colder than many solar system comets. Conversely, if water dominates near modest solar distances, it looks more familiar. Either way, the ratios among key volatiles help diagnose where in its natal disk 3I Atlas likely formed relative to snow lines, and whether its chemistry reflects a quiescent region or one processed by energetic radiation. Dust properties are equally revealing. Polarimetry, colour measurements, and tail dynamics constrain grain size distributions and porosity. If the dust aligns with highly porous aggregate-like grains, that points toward gentle growth and limited compaction. If grains appear more compact, with distinctive scattering behaviour, that suggests different coagulation or thermal histories. Tail curvature and thickness, interpreted through radiation pressure modelling, yield typical grain sizes and ejection speeds. Those in turn reflect near-surface cohesion, gas flux, and vent geometry. A consistent picture across wavelengths, slightly reddened dust colours, a specific polarisation phase curve, and a particular mix of grain sizes lets scientists place 3I Atlas on a map relative to well-studied comet families, while noting any systematic departures. Dynamics connect the object to planetary system architecture. The speed and direction of approach, together with population statistics from surveys, constrain how efficiently planetary systems eject planetesimals. High ejection efficiencies usually imply interactions with giant planets or dense stellar birth environments. If the inferred space density of objects like 3I Atlas is high, that supports scenarios where planet-forming disks shed large numbers of solids into interstellar space. If it's low, ejection may be rarer or the size distribution different than expected. 3I Atlas therefore helps calibrate how common extrasolar comets are, and indirectly how typical our solar system's history might be. The activity dynamics coupling is another reason for enthusiasm. Because 3I Atlas is active yet shows only limited or tightly constrained non-gravitational accelerations, it allows researchers to test momentum transfer models in a new regime. Matching the observed coma and tail to the lack or smallness of orbital recoil refines estimates of mass, active fraction, and jet symmetry. That cross-constraint is rarely this clean. Independent measurements, astrometry for dynamics, imaging for morphology, spectroscopy for gas, interlock to bound fundamental properties like nucleus size, density, and surface heterogeneity. Surface physics and thermophysical behaviour are front and centre. The way activity turns on with decreasing solar distance, the presence or absence of outbursts, and the stability of jet features all reveal how the upper centimetres to metres of material respond to heating. A durable dust mantle implies evolutionary processing that can suppress activity until vents or cracks open. A highly porous surface with low thermal inertia encourages rapid diurnal variability. Tracking 3I Atlas across its approach and recession allows tests of these models in an interstellar context, asking whether its near surface resembles typical long-period comets or shows systematic differences that might trace back to a different stellar spectrum, disk chemistry, or irradiation history. Comparative planetology is the broader frame. With 3I Atlas, scientists can contrast three pillars: the first interstellar object that lacked an obvious coma, the second that behaved like a typical comet, and now another active visitor with intriguing mass and activity characteristics. Patterns that repeat across interstellar comets, such as volatile ratios, dust porosity, or the prevalence of jets, may indicate common formation pathways across many planetary systems. Clear differences, on the other hand, argue for diverse disk conditions, migration histories, and irradiation environments. Either outcome is informative. Sameness means universality. Differences map the parameter space of planet formation across the galaxy. Chemistry at the complex organic level is a further hook. Even at low signal, spectral features in reflected or emitted light can hint at carbon-rich compounds in the dust and gas. While detailed molecular inventories from Earth are challenging, broad indicators of organic richness, together with dust colour and polarisation, inform how far prebiotic complexity might progress in cold, radiation-processed ices before incorporation into larger bodies. If 3I Atlas shows an organic signature comparable to, or distinct from typical comets, it adds a data point to discussions about how common complex organics are outside our system. Rotation and mechanical properties are in play as well. Detecting a stable or slowly varying rotation period through jet repetition or carefully coma-corrected light curves constrains the moment of inertia and internal strength. Minimal spin-up during high activity suggests either a higher mass, symmetric venting, or both. Any fragmentation or lack thereof under thermal stress sheds light on tensile strength and cohesion. These mechanical clues are hard to glean from distant objects, so an active interstellar visitor like 3I Atlas represents a rare opportunity. Population synthesis benefits directly. Each well-characterized interstellar object anchors models that predict detection rates for current and future surveys. The measured brightness evolution, activity level, and skyplane motion of 3I Atlas help stress test survey pipelines, refine completeness estimates, and improve strategies for catching faint inbound objects earlier. Better early detection would enable more comprehensive characterization, longer spectroscopic time series, deeper polarimetry, and coordinated multi-wavelength campaigns, so every success today improves the science return for the next visitor. Finally, there is a practical mission-facing angle. The more we learn about how often objects like 3I Atlas appear, how fast they move, and how their activity behaves, the better we can design rapid response observation programs and, eventually, interception concepts. Even without sending hardware, coordinated observations across ground-based facilities and space telescopes can now assemble multi-band, time-resolved datasets that were impossible a decade ago. 3I Atlas presents precisely the kind of target that pushes those networks to their limits and, in the process, upgrades the community's toolkit. In short, 3I Atlas is a laboratory for testing ideas about planet formation, disk chemistry, dust microphysics, volatile transport, and small body mechanics under conditions that did not occur in our own solar system. Its activity provides gas and dust diagnostics. Its dynamics bound mass and jet symmetry. Its light teaches us about grains and surface layers. And its mere existence constrains how often planetary systems eject material into the wider galaxy. That breadth, one object informing so many subfields at once, is why scientists are keen to extract every possible measurement while it's here. Are more interstellar visitors coming after 3I Atlas? Almost certainly yes, and likely more often than in the last decade, because three trends are colliding: deeper, wider surveys, faster, smarter detection pipelines, and a global follow-up network that learns with each new object. Survey depth is the first lever. The faintest objects a survey can see, its limiting magnitude, sets the effective discovery volume. Push the limit a bit deeper, and the searchable volume expands dramatically. A 1 magnitude gain roughly increases the discovery volume by a factor of approximately 2.5 to 3, depending on geometry and how brightness falls with distance. Interstellar objects move fast and are visible for only a short slice of their trajectories, so raw depth directly converts to more chances to catch them before they brighten near the sun or vanish into twilight. Field of view and cadence are the second levers. Wide cameras that scan the whole accessible sky every few nights, or even nightly, create the tracklets needed to recognize a fast mover. Cadence matters because interstellar objects don't politely stroll, they streak. If the sky is revisited frequently, software can link short trails into a coherent path and flag the orbit as hyperbolic early, when follow-up time still exists. This is crucial. Classifying an object as interstellar often requires a few days of astrometry to nail a reliable eccentricity above 1.0. The sooner that happens, the more telescopes can jump in with spectroscopy and high-resolution imaging. The pipelines themselves are the third lever. Traditional moving object software optimized for near-Earth asteroids struggles with very fast, faint trail detections. Modern routines now search for streaks, not just points. They measure trail length, angle, and brightness along the streak to estimate on-sky rate and filter out satellites and artifacts. Machine learning classifiers can learn the difference between a cosmic ray, a satellite glint, and a fast astrophysical streak, reducing false positives so humans can focus on real candidates. Better linking across nights and across observatories also shortens the time between "there's a weird streak" and "this orbit is hyperbolic." Even with these improvements, selection effects are strong. We're far more likely to discover interstellar comet-like bodies than mere inert rocks of the same size, because an active coma and tail add cross-section and boost brightness. That means 3i Atlas, an active object, is exactly the type we'll preferentially find. Inert interstellar asteroids exist, but they will remain biased against detection unless they pass unusually close to Earth or are comparatively large. Recognizing this bias is important when translating discoveries per year into how many are actually out there. Sky geometry introduces additional biases. Discoveries favor objects entering the inner solar system at high solar elongation, comfortably separated from the sun on the sky, and moderate phase angles, where trailing losses are manageable and backgrounds are dark. Conversely, many inbound trajectories approach near the sun's glare and remain effectively unobservable until too late. Planetary configurations matter too. Gravitational focusing by Jupiter can bend some interstellar paths inward, enhancing discovery chances in certain epochs, while also imparting deflections that complicate early orbit fits. On the dynamic side, the interstellar flux depends on how efficiently planetary systems eject leftovers from planet formation. Giant planets, migrating resonances, and stellar encounters in birth clusters all help sling planetesimals into interstellar space. If ejection is common, and the first few detections suggest it isn't rare, then the galaxy is filled with a broad-sized distribution of wanderers. Our telescopes skim only the bright tail of that distribution. As surveys improve, the detection rate should climb from once in a while toward occasional but routine, with periods of multiple detections in a single year not out of the question once deeper, faster surveys reach steady operations. Follow-up infrastructure is now a force multiplier. The moment a candidate looks hyperbolic, alert networks can request rapid astrometry to stabilize the orbit, trigger spectroscopy to sniff out volatiles, and schedule high-resolution imaging to search for jets and set nucleus limits. Coordinated campaigns distribute the load across longitudes and hemispheres, covering gaps caused by daylight and weather. This relay race dramatically increases the scientific return during the short window when an interstellar object is bright enough to study. Archival searches, recoveries, quietly boost the detection rate after the fact. Once an orbit is known, teams comb through past images to find earlier, fainter scuds appearances of the same object near the inbound leg. Each recovery extends the arc, sharpens the orbit, and, in some cases, elevates borderline candidates into confirmed interstellar status. Better access to calibrated, time-stamped image archives and software to search them efficiently makes this strategy more potent every year. Infrared capability is another key upgrade. Cold, dusty Comey can be underluminous in reflected sunlight yet emit strongly in thermal infrared. Space-based infrared surveys will complement optical searches by detecting objects that are too dark or geometrically unfavourable in visible light. For interstellar comets, IR measurements also constrain dust temperatures and sizes, improving mass loss estimates and, indirectly, the dynamical inferences about nucleus mass and jet efficiency that have become central for 3i Atlas. Expect variety among future finds. Some visitors will look like classical comets, others more like low-activity bodies with only a weak halo. Volatile ratios may differ markedly, reflecting formation beyond different snow lines in their natal disks. Dust polarimetry could reveal more compact grains in one object and ultraporous aggregates in another. Dynamical properties will also vary. Some will have higher or lower excess velocities. Some trajectories will favour southern observers. A few will pass unusually close, enabling radar experiments or stellar occultations to set sharp size limits. Each subtype helps fill out the population map and teaches us which kinds we are missing due to survey biases. Capture is unlikely but worth mentioning. Temporary gravitational capture by a planet or by the Sun is theoretically possible for the slowest interstellar entrance under very specific geometries, but the typical speeds make permanent capture rare. Practically, we should expect most visitors to be swift, one-pass events like 3i Atlas. That's why the detection to characterization pipeline must be rapid. Miss the week when geometry is favourable and the science opportunity is gone for good. From a practical observing standpoint, the community now treats possible interstellar as a specific mode. Telescopes prepare non-sidereal tracking for high on-sky rates. Observers select exposure times that balance signal against trailing. Photometric apertures and coma modelling choices are standardised so results can be compared across teams, and polarimetry or narrowband gas filters are cued if the object brightens enough. This readiness did not exist a few years ago at its current level. Each new visitor, including 3i Atlas, has pushed the system forward. Finally, detection rates are not just a function of technology, they also reflect how we prioritise time. Interstellar candidates now jump to the front of the queue precisely because they are rare and fleeting. That cultural shift, combined with deeper surveys and smarter software, is why the answer to "are more visitors coming home?" is yes in two senses. Yes, in the physical sense that many such bodies are passing through the inner solar system each decade, and yes, in the practical sense that we are increasingly capable of noticing them. As those two curves, true flux and human capability, continue to overlap more, the sample size will grow, the statistics will stabilise, and we'll be able to place 3i Atlas within a much richer catalogue of worlds from other suns. 3i Atlas is not expected to be a naked eye spectacle. For most observers, it will present as a small low-surface brightness fuzz that demands dark skies, careful planning, and, ideally, optics. Binoculars will rarely be sufficient unless conditions and geometry are unusually favourable. A telescope in the 15 to 20 centimetre aperture class, 6 to 8 inches, under dark, transparent skies is a sensible minimum for visual detection. Larger instruments improve your chances of seeing a compact coma, and, with patience and averted vision, hints of a tail. Electronically assisted viewing or imaging and live stacking, with even modest gear, can reveal far more than the eye. Start with geometry. Your ability to see 3i Atlas is dominated by three distances, angles. Heliocentric distance, r, how far it is from the Sun, geocentric distance delta, how far it is from Earth, and solar elongation, the angle between the object and the Sun on your sky. Good observing windows require sufficient elongation so the target is well away from twilight glare. Think comfortably above approximately 35 to 40 degrees from the Sun, and high enough in altitude to minimise atmospheric extinction. Aim for greater than 30 degrees elevation if you can. Phase angle, Sun object observer. Influences brightness and tail appearance. Moderate phase angles can enhance dust scattering, but very large phase angles often coincide with low elongation and poor visibility. Expect the apparent speed to increase as 3i Atlas approaches the Sun and slow on the way out. Fast apparent motion means two things for imagers. 1. If you track at the sidereal rate, the comet will trail. 2. If your mount supports non-sidereal tracking, custom RA/DEC rates. Use it to keep the nucleus sharp. A practical exposure limit when tracking on the stars is set by the trail budget. Compute to trail length on the sensor, pixels approximately equals rate on sky in arc seconds per second, times exposure in seconds, divided by image scale in arc seconds per pixel. Keep trail length below approximately 1 to 2 pixels if you want round stars in star-aligned stacks. If you are comet aligning, you can tolerate trailed stars and prioritise a sharp coma. Many capture programs can dither, and later align either on the stars or on the comet's photocenter. Plan both products because they serve different purposes, pretty picture versus science-friendly measurement. For visual observers, treat 3i Atlas like a faint diffuse galaxy. Dark adaptation matters. Shield stray light, avoid phones, and use averted vision. Start with low to medium magnification, exit pupil approximately 2 to 4 mm to maximize surface brightness. Once you detect the coma, experiment with slightly higher magnification to probe the inner condensation or jet asymmetries. Nebula filters UHC/O3I are not useful. Comets are broadband reflectors plus gas emission, and these filters usually dim the view. A polarizing filter can sometimes increase contrast under bright skies, but results vary. Light pollution is a serious handicap because comae have low surface brightness. On the Bortle scale, push for Bortle 4 or darker if possible. Under bright urban skies, switch to imaging or EAA. A sensitive camera, uncooled or cooled, on a small refractor 60 to 100 mm, with short repeated exposures and live stacking will beat visual detection in the city by a wide margin. Use raw capture, fixed white balance, and avoid in-camera noise reduction that smears faint detail. For DSLR mirrorless imaging through their lenses, a 135mm to 300mm lens gives a good compromise between field of view to show tail structure and scale to resolve the coma. Shoot wide open or 1 to 2 stops down for sharpness. ISO 800 to 3200 depending on sensor and temperature. Keep single sub-exposures short enough to limit trailing, given the on-sky rate. Compensate with quantity and stacking. Through telescopes, luminance, clear, is most efficient for signal. If you have a filter wheel, RGB adds colour, but costs photons. Consider L for structure, plus a few short RGB sets for colour. Narrowband comet filters, e.g. isolating CN or C2, are for advanced use and require strong gas emission. For most amateurs, broadband luminance will show the most. If your mount supports non-sidereal tracking but not custom rates, you can guide on the comet itself. Many guiding tools allow you to lock on a moving target. This keeps the nucleus crisp while stars trail. Capture 2 sets, a comet-aligned stack, sharp coma, trailed stars, and a star-aligned stack, round stars, trailed comet. The comet-aligned stack is best for measuring coma shape, inner jets, and tail opening angle. The star-aligned stack is friendlier for aesthetic presentation and background star colour. To plan sessions, you will need nightly ephemerides, right ascension, declination, altitude versus time, solar elongation, and on-sky rate. Generate those from your preferred ephemeris service or planetarium software, and pay attention to hour-by-hour altitude. Favour times when 3i Atlas is highest, when the moon is below the horizon or at small phase, and when the target is far from the dawn-dusk glow. If the predicted path hugs the ecliptic near bright star fields or the Milky Way, confusion increases. Verify field stars with a chart to avoid mistaking a condensed galaxy or unresolved cluster for the comet. Magnitude expectations for comets are notoriously uncertain because dust production can vary. Photometric predictions often use a law of the form m equals h plus 5 log delta plus k log ER, where h is an absolute magnitude and k the activity index, sets how brightness scales with solar distance. Treat these as rough guides. A dust-rich coma can brighten the object while spreading light over a wide area, making surface brightness low, and the visual view underwhelming even when the total magnitude looks promising on paper. That's why imaging, which integrates longer and stacks, routinely outperforms the eye for comets like 3i Atlas. If you want to contribute data, basic comet photometry is within reach. Use a circular aperture centered on the coma and a sky annulus for background subtraction. Keep your aperture size consistent in arc seconds on the sky between nights, so results are comparable. Differential photometry against nearby catalogue stars with well-known passband magnitudes reduces systematic errors. Report the aperture, radius, filter, exposure details, and conditions alongside the magnitude estimate. For dust production trends, some observers compute a FRHO from their data. Doing this reliably requires careful calibration, but even repeated consistent measurements in a single band are valuable for tracking changes. Morphology studies benefit from simple, careful processing. After calibration, darks, flats, bias. Try a gentle unsharp mask or divide by a 1/row profile to enhance jets and fans. Avoid over-processing that invents structure. Measure the tail's position angle, degrees east of north, and any changes over hours or days. Note whether there is a straighter trail aligned with the orbit in addition to an anti-solar dust tail. Record the coma diameter in arc minutes at a fixed surface brightness threshold if your software supports isophoto overlays. These are concrete descriptors others can compare. Safety and practicality. Never attempt to observe 3i Atlas at very small solar elongations. Do not point optics near the sun without proper solar filters. Low altitude views are degraded by extinction, dispersion, and turbulence. If the object sits under approximately 20 degrees elevation, it will be much harder than its nominal magnitude suggests. Dew control, heaters or shields, preserves contrast during long sessions. Allow optics to reach thermal equilibrium to avoid tube currents that blur the coma. Collimation matters in reflectors. A tight, symmetric stellar PSF helps when you are trying to separate a slightly condensed nucleus from the inner coma. Hemispheric and seasonal considerations apply. Depending on its inclination and node geometry, 3i Atlas may favour one hemisphere for a given month, and then shift to the other on the outbound leg. If you can travel to a darker site with better altitude for the target, that single change can double your effective signal. In all cases, plan around the moon. Comets dislike moonlight. A waning crescent in the pre-dawn or a waxing crescent in the evening is manageable. Gibbous phases will flatten subtle coma gradients and drown faint tails. If you are attempting spectroscopy, even a low dispersion grating in front of the camera sensor can capture broad emission from the coma superimposed on the dust continuum. Keep exposures short to control trailing, then stack in the comet frame. Calibrate with the reference star spectrum in the same setup. Spectroscopy is demanding at the signal levels typical for 3i Atlas, so choose bright phases and maximal altitude. Set expectations honestly. Visually, you are likely to see a soft, slightly condensed haze, possibly with a brighter core and an asymmetry or elongation indicating a tail direction. In images, live stacks will reveal much more. Fan-like dust tail, curvature due to radiation pressure, and potentially subtle jets close to the nucleus. If forecasts suggest it remains faint, consider making your observing goal a time series. Even if each frame looks modest, the scientific value lies in how its brightness, size, and tail geometry evolve over nights. Finally, keep meticulous notes, record date and time, UTC, site and conditions, transparency, seeing Bortle class, equipment, filters, exposure details, and any processing steps. Note the object's altitude, elongation, and on-sky rate used for planning. Consistent logs let you compare your own results across sessions and make your data useful to others. 3i Atlas is a fast visitor. A handful of well-planned, carefully documented sessions will teach you more than a dozen casual attempts. If you approach it like a faint galaxy with a clock ticking, your chances of success and the quality of what you capture go up dramatically. What happens next is a coordinated push to lock down the physical and dynamical properties of 3i Atlas, while geometry is favourable and activity is evolving. The priorities are clear. Tighten the orbit with extended astrometry before and after peak activity. Test for non-gravitational accelerations at the higher sensitivity. Constrain the nucleus size and active fraction with high-resolution imaging and coma modelling, and measure volatile and dust production rates across a range of solar distances to pin down the drivers of activity. On the orbital side, the plan is straightforward. Accumulate precise positions from many observatories over the widest possible time span and viewing geometries. Those data sets reduce the covariance on the hyperbolic solution and make smaller long-track accelerations, if present, stand out from noise. Teams typically publish both a purely gravitational solution and one or more solutions that include candidate recoil terms scale by solar distance. As the arc length grows and the object swings through different phase angles, the best fit model will converge. If the orbit continues to fit without measurable rocket-like terms despite visible coma, the lower bound on mass strengthens. If a coherent drift appears, the permissible mass range shifts accordingly. Rotation and jet geometry are the second major track. Repeated imaging sequences will be analysed for changing jet position angles, corkscrew patterns, or repeating fan structures that reveal the spin period and pole orientation. Even course period estimates are powerful. When combined with any size constraint, they place limits on the moment of inertia and the efficiency of outgassing torques. A stable period through the highest activity phase would be consistent with a larger moment of inertia, more mass and/or larger radius, or with symmetric venting. Measurable spin-up would push interpretations toward asymmetric jets and a lower mass-to-area ratio. High-resolution imaging, either from space or from large ground-based telescopes, will aim to separate the inner coma from any unresolved nuclear signal. The standard workflow is to model the coma with a parametric profile, subtract it, and test whether a point-like core remains above residuals. Translating that residual into an effective diameter then requires assumptions about geometric albedo and phase function. Even if only upper limits are obtained, pushing those limits downward matters. A small upper limit combined with a lack of orbital recoil would argue strongly for a dense, compact body or a very low active fraction. Spectroscopy and narrowband photometry will map the volatile budget and its evolution. Visible near UV spectra constrain classic radicals in the coma. Near-infrared spectra target parent molecules that drive activity at larger solar distances. The goal is a time series of production rates for the dominant species and their ratios. Those ratios diagnose which ices control the activity at each stage, which in turn sets expectations for jet speeds and momentum transfer. If 3I Atlas exhibits relatively strong low-temperature volatiles compared to water, one would expect earlier activity onset and potentially different jet kinematics than in water-dominated comets at the same distance. Dust diagnostics proceed in parallel. Broadband colours and polarimetry track grain composition and porosity. Tail morphology and curvature, interpreted with radiation pressure models, yield characteristic grain sizes and ejection speeds. Photometric proxies like F4AQ provide a uniform way to compare dust production between nights and with other comets. These dust metrics matter dynamically. For a given gas production rate, a dust-rich coma can carry significant additional momentum, increasing the expected non-gravitational acceleration unless mass or symmetry counters it. Cross-comparing dust indicators with the astrometric non-detection, or detection, of recoil will be a central test of the more massive than expected picture. Thermophysical modelling links the observations to surface physics. By fitting the timing and amplitude of activity against solar distance, researchers infer thermal inertia, depth of volatile layers, and whether a dust mantle throttles sublimation. Models with localized vents are compared to models with quasi-isotropic activity. Each produces distinct predictions for coma profiles, jet repeatability, and torque history. The favoured model will be the one that simultaneously matches the light curve, the morphology, the volatile production rates, and the non-detection of the orbital recoil. Occultation attempts are a wild card with high payoff. If the predicted path of 3I Atlas crosses a sufficiently bright star, coordinated observers can time the tiny dip in starlight to measure the nucleus size with kilometre-scale precision. The coma complicates matters by adding scattered light, but careful choice of star, filters, and high-speed cameras can mitigate this. Even a non-detection with useful limits, no dip deeper than a threshold, would refine the upper bound on diameter. Thermal infrared observations, when feasible, add an independent constraint on the effective emitting area of dust and, in rare best-case scenarios, on the nucleus itself. Thermal fluxes, together with plausible temperature models, put bounds on the total cross-section of warm material. Comparing those bounds with reflected light estimates helps separate the contributions of dust and nucleus to the total brightness. On the data analysis side, expect iterative refinements rather than a single final answer. Early reductions will provide preliminary production rates and orbit fits. Subsequent reprocessing with improved flat fields, better coma subtraction, and merge multi-facility astrometry will tighten uncertainties. Morphology analyses will evolve from single-epoch images to time-resolved maps of jet behaviour. Tail models will progress from simple synchrones/syndanes to full Monte Carlo dust dynamic simulations with realistic grain property distributions. Each iteration narrows the allowed parameter space for nucleus size, density, active fraction, jet speeds, and pole orientation. Risk factors and failure modes are part of the plan. If activity spikes unpredictably, or the object experiences an outburst or partial fragmentation, coma modelling and photometry can be thrown off for days. Conversely, a sudden decline in activity near closest approach would reduce the chance of detecting gas species and complicate mass loss estimates. Observational geometry may also close quickly if solar elongation drops or if moon phase and weather wipe out key windows. That is why redundancy, multiple instruments, multiple longitudes, and diverse techniques is built into the observing campaigns. What the community hopes to have at the end of this phase is a coherent, mutually consistent set of constraints. An orbit history that either does or does not require non-gravitational terms above tight thresholds, a rotation period, and perhaps a spin axis orientation derived from repeating jet features or a coma-corrected light curve, volatile production curves as a function of solar distance with uncertainties and systematics quantified, dust production and grain property inferences from photometry, polarimetry and tail modelling, and the best available bounds on nucleus size from imaging, thermal measurements, or an occultation. From those, a posterior distribution on mass and density can be assembled that transparently shows what is driven by data and what is driven by assumptions. After the main observing window closes and 3i Atlas fades, attention shifts to synthesis and population context. The derived properties will be compared against solar system comets and the other interstellar visitors to see whether 3i Atlas is typical or an outlier. If its inferred mass-to-area ratio and activity pattern are unusual, that will inform models of how planetary systems eject bodies and how those bodies survive interstellar processing. If instead the object slots neatly into familiar ranges once geometry and symmetry are handled correctly, that outcome is equally valuable. It signals that early massive impressions arose from understandable selection effects and modelling choices. There is also a methodological legacy. The tools, pipelines, and observing playbooks refined on 3i Atlas directly improve readiness for the next interstellar target. Faster candidate vetting, better non-sidereal tracking templates, standardized comet photometry protocols, and shared morphology processing scripts mean the next object will be characterized earlier and more completely. In the longer term, these lessons inform studies of rapid response mission concepts. Viable interception requires very early discovery and instantaneous planning, so understanding typical approach speeds, brightness evolution, and activity variability is essential, even if such a mission is not feasible for 3i Atlas itself. In sum, the next phase is an evidence-gathering sprint focused on 5 pillars: orbit precision, rotation and jet mapping, volatile and dust production time series, nucleus sizing and thermophysical interpretation. Each pillar cross-checks the others. When the dust literally and figuratively settles, the community expects to know whether 3i Atlas truly carries more mass for its brightness than a conservative comet analogue would suggest. How its surface and near-surface release material, what its dominant ices are, and how those facts fit into the growing picture of small bodies formed around other stars. Thank you for spending this time with me. Take a slow breath in and let it out. If you made it all the way here, you now have a clear map of what makes 3i Atlas special. An interstellar visitor on a hyperbolic path, an active comet-like body that vents gas and dust, and a puzzling mass story that's being tested from every angle. We've looked at how its orbit is refined, how jets and dust reveal the surface, why non-gravitational accelerations, or the lack of them, matter, what scientists hope to measure next, and how you can plan a realistic observing session. Even if you never point a telescope at 3i Atlas, you've learned how to read the signs, what elongation, phase angle, and activity mean, and how all those threads tie back to the simple question, what is this object, really? As we close, remember that 3i Atlas is not just a moving dot in the sky. It is a messenger from another star system, carrying the chemistry and physics of a place we will likely never visit. It has travelled for millions, perhaps billions of years across the void, and for just a brief moment it passes through our neighbourhood. To witness it, even through data, even through shared knowledge, is to stand at the edge of something vast. If you enjoyed this journey, let me know where in the world you're watching from. Share your thoughts, your skies, your questions. Did you feel awe at the idea of dust grains born around another sun scattering light above us? Did you pause at how scientists can weigh a world not by touching it, but by noticing what doesn't happen in its orbit? Or did you simply enjoy the calm of sitting with a mystery too large to solve in one night? Take this feeling with you, that science and wonder are not separate but partners. The careful measurements, the equations, the graphs are one side, the quiet sense of scale and beauty is the other. Together they let us see 3i Atlas for what it is, fleeting, distant, but deeply meaningful. So until the next voyage, keep looking up. Whether you see stars, clouds, or city lights, remember that interstellar travellers are always out there, and one day another will come. And when it does, we'll be here again, breathing slowly, asking questions, and marvelling at the answers. Good night.